All right, example 3, the last example of Calc 3. Determine the flux of this vector field F through an arbitrary surface S. Okay, so to do this, determine flux through an arbitrary surface. So let's think about this. So again, flux, let's think about this. Flux of a vector field through some surface S, flux is always a vector surface integral of that vector field over the given surface. Okay, but they say that this is an arbitrary surface. So this means arbitrary, you can just read this as any surface. So we don't actually know what this S is, right? This could be anything. So if this is allowed to be anything, and we're supposed to be able to answer this problem, this must mean that the answer to this does not depend on S. Okay? Well, if it doesn't depend on S, it's surface independent, in other words. We did learn about that. So remember that the flux of a vector field over a surface, this can be independent in a couple ways. Well, the one way is if F is the curl of some other vector field, right? If F is the curl, so this is like a thought I'm having here. So if F is the curl of some other vector field, then we know that the surface integral over S of F dot ds, in other words flux, is equal to the curl of A dot ds, which then, using Stokes' theorem, can be rewritten as the line integral around the boundary of S, A dot dr. But again, if this is an arbitrary surface S, that means the boundary of S could be anything also. So the only way that this doesn't depend on this is if, well, yeah, the only way that this could happen is if this is path independent and it only depends on the endpoints. If it only depends on the endpoints, and this would mean that A would have to be the gradient of some scalar function. Okay? That's the only way this could happen. That's the only way this could happen based on what they've given us so far. So this would have to be true. Okay? So then we could say that this is just F on the boundary of S. So if you watch the one video I made, I did talk about something a little bit outside the scope of this class, but it was an interesting connection that ties together all of the different theorems. And it was something called the exterior derivative, which is really what unifies usual differentiation, gradient, curl, and divergence all together. And it has a property that if you apply the exterior derivative to a certain object, something called K-forms, which are what effectively we can think of vector fields and functions, and we can think of them all as different K-forms if we'd like. We find out that if we apply the exterior derivative successively, so 2 times, we get 0. So notice here what we've done so far is we've arrived at the conclusion that the only way this problem makes any sense is if A is the gradient of F and A And so effectively, this only makes sense if f is the curl of a and a is the gradient of f. So in other words, f must be the curl of the gradient of some scalar function. Well, this only makes sense. Well, first of all, right here, this is applying two exterior derivatives in a row. So this would have to be 0. This would have to be the 0 vector field. Okay. So one way we can check this is, we've talked about this. This only makes sense if, or we talked about this in a previous video, that you can tell that this is the curl of some A if, so f is the curl of some vector field A if the divergence of f is equal to 0. That would be true. Okay, but that's going a little bit outside the scope of this problem. It's kind of relying on some more sophisticated techniques. If we just go ahead and think about what we could do here, we can use the divergence theorem. The divergence theorem says that we can, if S is some arbitrary surface, right? And I'm going to go ahead here and insert closed surface because the divergence theorem says we need it to be closed. So let's just pretend that was added in there. Need to rewrite these notes. Divergence theorem says that we can interpret at least the surface as, we can interpret S, the surface, as the boundary of some solid volume in three-dimensional space. So the divergence theorem would be the triple integral over W of the divergence of F. And we can see that this condition still arises even if we don't think about the exterior derivative and all those little extras that I had in the one video. But it does link them, and it's a nice way to build intuition, I think. So if we go ahead and take the divergence of this vector field, we end up getting the following. So the x partial of this is y squared, plus the y partial of this is 0, plus the y partial of this, or excuse me, not the y partial, excuse me, the z partial of this is negative y squared, which is the triple integral over w of 0 dv is just 0. And that concludes Calc 3.